Good morning, everybody. We're group number 5. Today we're going to be presenting our senior design project, Ocean Hydropower Harbor Station. My name is Horta.
I'm Medina.
And I'm Sosa. There are three big factors that influenced our choice in our project. The first one was the abundant amount of energy we consume on a regular basis. According to the U.S. Energy Information Administration, total worldwide energy consumption is steadily increasing, as can be shown in this table. These readings are in quadrillion of British thermal units. If we look at 2012 alone, and convert the total amount of energy consumed from British thermal units to gigawatts, it will give us a rough estimate of about 155 billion gigawatts of energy consumed in 2012 alone. The lack of access to sustainable energy is another big problem. This image depicts a nighttime view of the regions that have access to sustainable energy and those that don't, as is the case for North India and the Philippines. Increasing population also plays a big role in energy consumption. It is estimated that in the next 50 years there's going to be a total of 2 billion new individuals living among us. If each one of these individuals uses just one 50-watt light bulb throughout the course of their lifetime, that will add up to 100 gigawatts of new energy that we have to account for. These three topics that we just talked about, the abundant amount of energy we use, the lack of sustainable energy, and the increase in population, motivated us to find a sustainable, feasible way of harvesting energy.
We went into our literature survey looking at existing technologies for this field. We looked into current turbines that work exactly like wind turbines in semi-desert environments. Into turbine generating units, which is the same thing as same technology as current turbines, but in both. We looked at Calamus, which is in commercial use right now in Europe, off the coast of Scotland, and it works by the links moving up and down through waves, causing pressure and harvesting energy. And we looked at also wave riding arms, which these particular ones are off the coast of Brazil and work with the force of the waves pushing the arms up and harvesting energy as well. We summed up all these existing technologies, and we saw that they're very bulky. They're very bulky systems. So we were looking into a unit much smaller than any of these. We then researched 2 different types of ways of harvesting that energy from the ocean, particularly from waves. It's either from wave currents or wave heights. We looked into wave heights from around the world. We saw that there does exist wave height differentials all around the world, and we saw the potential energy in this height, which resulted into the independent variable that we would design our prototype and do the testing with.
Taking consideration the technologies are out there, we want to come up with a simple design. As you can see, we had 3 main components in our design. We had a retractable cable, which is purposed to be mounted on the seafloor, and followed by a shaft connected with a torsional spring, all guided together with a gearbox when in motion and the cars are generated.
We went to a theoretical analysis and looked at the forces that we would need to take into consideration before we did a prototype analysis. We looked into a buoyancy force, our weight force, and the spring force, which represents our retractable cable. Of course, our delta, which is what we looked into from our research, would come in from the wave heights around the world. That linear energy would then be transformed into rotational energy through the use of the torque, the radius coming from the retractable cable, and then we calculated our angular velocity by time of the torque and the moment of inertia of our system. We then transformed that rotational energy into mechanical energy with a simple reverted gear train, which we have in our gearbox, and this is an exact replica of what we have. And we calculated different gear ratios that we wanted to implement into our design. We then transformed that mechanical energy finally into electrical energy through the use of alternator.
Going from our conceptual design and our proposed design pretty much follow along. As you can see on the left, we have this black box which inside keeps our retractable cable and our torsional spring, followed by a shaft and connected to our gearbox, which powers our alternator. On the figure to the right, you can see some of the components on the inside, which are the gears, the bearings, and the actual alternator. And on the bottom side, you can see the shaft that connects.
We designed our structural design in the most feasible way possible. There are 4 main components to a structural design. The housing unit, which houses all the sensitive components of our design. Inner tube, which provides the proper buoyancy to keep keep our design afloat, a lid that seals the housing unit from the top, as well as provides the shape to our overall structure and houses the solar panel, and a cover to add an extra layer of protection to the device.
We looked into applicable standards before we went into the construction of our prototype. We looked into the Bureau of Ocean Energy Management and the Regulatory Commission. Pretty much for ocean and renewable energies, they're very lenient right now because these are rather new technologies. They said, they stated not to bring in the prototypes prefabricated and not fabricate anything in the ocean. They must be anchored to the ocean floor, and they need to have little to no impact in the environment. Also, we couldn't get in the way of any commercial or navigable waters. So with following these standards, we were pretty free in the sense that we didn't need any permitting or licensing to put our prototype into testing.
In the construction of our prototype, and the material that we selected was stainless steel due to the corrosion in the ocean water and the salt water in the ocean. As you can see, we pre-selected some of the key points of where our shaft is going to come out through, and also where our alternate is going to go. And on the left, you can see the actual shell of the gearbox and the height of it. Also, here are some of the components of the inside of the gearbox. And all together, we have the torsional spring and the retractable cable in the third figure.
As we mentioned earlier, the device consists of 4 major components. The housing unit is a 17-gallon galvanized bucket, which houses the gearbox, the generator, the battery, and the torsional spring and cable. All these components are mounted onto the housing unit through the use of custom plastic brackets, which are glued to the galvanized bucket through the use of epoxy. Our housing unit sits on a inner tube which protects it from getting hit by any boarding vehicles, as well as provides the proper buoyancy, and the lid seals the housing unit from the top. On top of the lid, there are 8 fins that provide the shape of our overall structure, as well as holds the solar panel in place. On top of the lid also sits the battery meter and the voltmeter for our generator. And the cover provides an extra layer of protection.
The design of experiments, we went through what we called our uncontrolled and our controlled environment. In our uncontrolled environment, we went out and we placed our prototype into the ocean. We recorded wave height on the boat that we were on, and we recorded the voltage output as well. However, because these, although we timed both of these readings, it was very difficult to simultaneously record the wave height and the voltage output. So unfortunately, this experiment resulted inconclusive. So we went into what we called our controlled environment, which we pulled the retractable cable at different displacements, and we recorded those voltage output, and then we can easily correlate the relationship.
This chart shows the results over 3 trials of our controlled experiment. As you can see, as the displacement increases, so does our voltage. And because our motor generates a current of 1 amp, and because power is equal to voltage times current, or power output is equivalent to our voltage output. These are a graphical representation of the 3 trials. As you can see, all of our results are very close to each other, and we need a minimum of at least 2 inches to start generating power. And like I mentioned earlier, as the displacement goes up, so does the voltage.
Our cost analysis consisted of all the components that it took for us to design the prototype and calculate the labor cost, which summed up to $683. By taking what energy costs in the United States, which is about 15 cents per kilowatt hour, we concluded that it would take about 237 days for this prototype to pay for itself.
In the future, we would like to continue testing on our prototype in different environments. As well, we would like to see bigger versions of our prototype that would allow us to use more solar panels, so we could include more add-ons such as GPS and LEDs to improve nighttime visibility. As well, a bigger prototype would allow us to use bigger gears, which would therefore allow us to use a higher gear ratio.
Taking the whole project in consideration, we're divided in 12 categories, knowing that everybody could best contribute in different categories. In this graph, you can see how we divided amongst ourselves to make this project more efficient.
Okay. We also evaluate our social and environmental issues. We had more pros and cons. For cons, we had obstruction of marine life and obstruction of navigable waters in both commercial and recreational usage. But we saw that through this design, we can increase ergonomics and economy in small communities. We saw the increase of education through the bringing about the technology of renewable energies, and even more so through ocean renewable energies, and the sustainability that this technology provides. And as global citizens, Florida International University, and as engineers, we became aware of the cost of electricity worldwide and the geological restrictions that exist of finding electricity. We also gained the perspective of knowledge of renewable energies and the sustainability that the ocean can provide. And of course, the engagement of clean energy uses and removing the dependency of limited resources such as fossil fuels.
Some more lifelong lessons that we learned from this project was the power of brainstorming. Also being able to work together in a project with the team members. And another thing is global awareness and emerging technologies coming for renewable energies and ocean power. In conclusion, we were able to achieve our motivation, which was able to design our project, test it, and be able to obtain good results from it. Even though we still know there's a lot of room for improvement and for better efficiency.
Questions?
The first comment I want to make is I think the presentation's exceptional. Very professionally presented. Your timing was really good. Some of the slides where you've got active slides moving in the presentation match the slides extremely well. So very impressed with that. Second, so from there I go into the question areas. Corrosion is your biggest enemy on a system like this. So talk to me about your system and what you would do differently to prevent potential corrosion. For example, you're using a galvanized bucket. I'm not sure that would last very long.
So definitely, especially in the ocean, salt is the biggest concern for corrosion. So one of our main concerns is the material, stainless steel. There's different derivatives of stainless steel, but stainless steel would be the most preferred selection.
Why wouldn't you use a plastic bucket? Let me go there.
Well, since we try to make it as usable as possible, the only plastic buckets that we could find were not very strong. So it would have to be a custom bucket.
Barrel, plastic barrel.
But you'd give her too big. I mean, you'd have to, it would increase your cost. But what we did try to do was we spray painted the galvanized bucket with a water-resistant material it's called Never Wet, but because it's galvanized, it didn't stick very well.
Yeah. Okay. What about your electronics? How did you protect your electronics from corrosion?
A lot of seating in the actual project, in the actual prototype. We have a lot of weather seals around it. Also, the gearbox itself is sealed. It should be shut off, but we had left the top portion of it open to be able to see the mechanisms and stuff. But in reality, it should be sealed. And should be
The worst part of saltwater corrosion is not in the water; it's above the water. So if you've got any kind of open access,
Yeah.
Right. So theoretically, our gearbox would be completely shut, and there would be lubrication in there as well.
okay. And then my last question is on energy transfer. How are you going to take the energy output of this system and actually make it usable?
So attached to the leads that we have in here, we would attach it to similar technologies. What they have is connecting cables completely submerged on the ocean floor, running and connecting it to an electrical grid, which would be onshore. There is a second option, which is another option that we had, was we have a battery in there. It would be less. It wouldn't be as direct as the electrical grid, as most renewable energies in the ocean have. But this would technically charge that battery, and you can take it out and put another one in, but it wouldn't be as effective as the direct contact with the cables running through the ocean floor.
During which part of the wave cycle are you actually generating your electricity?
At any moment. Through our design, we saw that we needed the minimum displacement of 2 inches. So if our retractable cable moved more than 2 inches, there was a voltage output. So at any type of any cycle, that's the great method of this design is the sustainability of that displacement at any moment.
So then is that while you're increasing the cable length or while you're decreasing as well?
Both, it runs both. It runs in both directions. As long as the cable is moving, the gears are spinning, and as long as the gears are spinning, there's electricity being harvested or energy.
So in your testing phase, did you have anything attached to that string? Because it seems as if you had some wave motion, but you didn't actually have a correlation between your distance or your displacement versus your power generation.
So right here, this little display right here, it's displaying the voltage output. So we got a GoPro, and we put the GoPro on the in front of the voltage, and we recorded that.
So what I'm going for is your actual cable,
Yes.
right? The one that is actually doing your transfer at that moment. If you were to, going back to that question, if you would do something different now, because in your control test, you were able to generate power, but not in the physical test, what would you do to that cable? Because what you're doing is the displacement between you, the buoyant equipment versus the cable to be, ever increasing at some point. What would you do differently? In that particular wire cable, so that it actually provides some drag between your fluid and the equipment, so that it actually generates power.
So your question is that how on the actual, in the actual ocean, how would it, well, the actual the cable is anchored to the floor, so according to the waves, it will be retracting.
And it did not provide any power whatsoever.
No, it did provide
It
power.
did. We just
They never
said
that
it was inconclusive because we couldn't present the data. We couldn't say that at a delta of half a foot, this was our voltage output.
Yeah, exactly. Like even though with the readings was 3 to 5 feet, you were, according to the voltage that we got, we couldn't correlate 2, 3, 4, 5 feet and to that voltage. So we did a control and distance. So if we pulled it 2 feet, we say, all right, about 2 feet of wave will produce this amount of voltage. Yes, we did produce voltage in the ocean.
I do have one more question. Did you ever check to verify that the system was to ground?
The
The
System
tank,
ground?
everything in your system?
Wasn't grounded.
So you don't know if you just created a big corrosion cell?
We didn't test that.